Hey folks, welcome to ByteBay. Today let's take a look at the concept of consistent hashing, which we must admit is a pretty powerful concept and is at the core of solving a fundamental problem for distributed systems, which has many real-world high-profile applications. The idea of consistent hashing was introduced in this 1997 paper, Consistent Hashing and Random Trees, and some of the authors of this paper, particularly Tom Layton and Daniel Levin, went on to form the content delivery network company Akamai, which till this day is a major player supporting approximately 35 to 40% of the total traffic on the internet. So before I start explaining the concept of consistent hashing by drawing a circle and some random servers and nodes like a million other YouTubers, let's pause for a moment to think what problem consistent hashing really tries to solve. Now, even to understand the problem that consistent hashing solves, we need to take a slight detour and briefly understand the concept of hashing. So what is hashing? Hashing is the process of transforming an input into an output using a hash function. That's it, guys. As simple as that. You provide one input to a hash function on one side and it converts that into another value on the other, which is the hash, and the entire operation is supposed to be idempotent. This means any number of times you provide the same input, it is always supposed to result in the same hash value. So how good is your hash? Usually that depends on how well you have written your hash function. But hold on, what do we mean by a good hash? We'll see that in a minute. For all our examples in this video, let's use this hash function, which is literally a function named hash. This hash function takes a string as an input and adds each character of the string into an integer variable, sums it up, and returns that as the hash. So as per our hash function, the string Samwise would result in hash value of 729, Frodo will result in 506, and Aragon will result in 714. Let's see an application of this concept. Let's consider these rectangles representing a continuous array of cells in memory. Let's call them buckets. What we really want to do here is that we want to store objects in these cells and we need to quickly find them based on a key. This is where hashing will help us. We use the string Samwise as the key, generate a hash 729 and store all the data for Samwise at memory cell location 729. So next time we want to fetch the data for Samwise, we pass the same key Samwise again, generate the hash again, get 729, and now we know that we need to look at memory cell number 729 to fetch all the data for Samwise, thus fetching the data quickly. Similarly, for Aragon, we store all the data at cell 714. For Frodo, we store all the data at cell 506. And for Edel, we store all the data at cell 374. But hold on for a second. What if there is another key whose hash value is same as that of an existing key? For example, what if we have a key Dale whose hash value is same as Adel? This, my friends, is called collision. So when two or more keys have same hash, a collision can happen. So to avoid this, we must write our hash function to be as efficient as we can. So what do we do in case there is a collision? Well, we store the data for Dale in the same location, but in a collection which we can iterate and fetch the objects. But how the heck is this thing related to distributed systems in any way? For that, let's see a sample system, or rather a server. All this does is it takes a username and gets the details for the user for that username by talking to a database. But before it returns the data to the user, it caches the data in memory because we do not want to talk it to the database every time we make the request. But over time, as we keep doing this, it saves more and more objects in cache, and eventually a day comes when we run out of memory in the server. What do we do now? Well, we go ahead and we buy 2 more servers. Why? 2 reasons. First, we have a hell lot of money, and second, because we want to horizontally scale our system so that we can cache more objects in our servers. But now the question is, when users request for a user's data and we cache it in one server, how do we know where we have cached that so that we can redirect the request to that particular server which has the data? Let's see a possible solution for that. Let's say we have 4 servers and a request comes in to get all the details for Samwise. We put a load balancer which has our hash function and we do a hash modulo 4. Why 4? Because we have 4 servers. This results in 1 and we forward the request to server 1. So every time a request comes for Samwise, we always go to server 1. Similarly, when a request comes for Frodo, we do a hash modulo 4 and get 2. So we forward the request to server 2. which talks to the database, returns the data for Frodo, and persists the data for Frodo at server 2. In the same way, we persist the data for Aragorn at server 2 and the data for Gollum, which has hash modulo 4, value of 0, at server 0. But we kind of did two mistakes. One, we forgot Gandalf, and second, we did hash modulo 4 to figure out the server to store data. Why is this a mistake now? Because now our logic is dependent on the number of servers. And now, if one of our servers go down, our logic will be affected. Now server 3 will become server 2 and we will have to do hash modulo 3 because now the number of servers is 3. So now when a request comes to fetch data for Samwise, hash modulo 3 becomes 0 and we forward the request to server 0 even though the data for Samwise is already present at server 1. Similarly, for Aragorn, we find out that the request should go to server 0 and for Frodo, the request should go to server 2. Alright, let's see another scenario. So what happens if none of our servers go down, but this time we need to add another server? Because guess what? Our existing servers are out of memory and we need another server to cache all our data. Now we need to do hash modulo 5 as we have 5 servers. With this logic, Frodo's data will now be cached in server 1 while all other existing keys get cached at server 4. This problem of getting keys cached in different servers even though they are already present in other servers is called rehashing. So what do we do to solve this problem? Consistent hashing to the rescue. So now that we are fully prepared to understand the concept of consistent hashing, let's go ahead and see how is this actually implemented. Let's consider an imaginary ring and put 4 servers on it, each 90 degrees apart from each other. Let's number these servers 0, 1, 2 and 3. Now in the example we saw earlier, we used the formula hash modulo number of servers to figure out the server which should hold the data. With the only problem being n could vary and change everything. Now in this design, let's replace n with constant k, which does not change. A simple choice in a circle would be 360 because moving a point by 360 degree makes a circle. So now, if we want to figure out where to store the data for user Samwise, we calculate hash modulo 360, which gives us 9. As 9 is between 0 and 90 degree, it would lie somewhere around here. Now in this design, what we'll do is we say to server 1, hey, can you go ahead and store the data for all the keys for which hash modulo 360 results in a number between 0 and 90 degree. So every key that lies between server 0 and 1 will be stored in server 1. Similarly, if we want to find the server which would store the data of Frodo, we calculate hash modulo 360, which gives us 146. As 146 is between 90 and 180 degree, it would lie somewhere around here. This time we ask server 2, hey server 2, can you store the data for all the keys for which hash modulo 360 is between 90 and 180 degree? So every key that lies between server 1 and 2 will be stored in server 2. We repeat the process for key of Gollum and the number hash modulo 360 now falls between server 2 and 3. So we store the data of Gollum in server 3. And we store the data for Gandalf on server 0 by the same logic. But are we sure this will work? What happens now if one server, say server 1, goes down? Let's see. Now for all the keys, value of hash modulo 360 stays same. So none of the values for Sam, Frodo or anyone else change. But who is now storing the data for Samwise? Well, we ask server 2, which was right after server 1 in clockwise direction. Dear server 2, the server before you is not with us anymore. Would you be kind enough to handle all the data and store it with you? And now we store the data which lies between 0 and 180 degree, actually all the data that lies between 0 and 180 degree on server 2. So while all this is good and we are not rehashing the keys again and all the keys stay in their original servers, this does increase the load on server 2. Now, if the load is too much on server 2 and if that is something that server 2 cannot handle, this may make server 2 crash. Then this will mean all the keys between 0 and 270 degree will now be stored in server 3. And if that crashes, then all the keys for servers will now go to server 0. And what happens if that too crashes? The entire system goes down. This effect is called cascading. Okay, let's see what happens when we add a new server. Say we add a new server between server 3 and 0. So all the data between server 3 and server 4 can now be stored in server 4, and all the data between server 4 and server 0 can now be stored in server 0. So more the number of servers, lesser the chances of cascading effect. But in real world production grade applications, organizations actually maintain clusters by adding more servers, which may themselves be using consistent hashing algorithm to map and store the data. Like this one, where a cluster of 3 servers is added at 90 degrees. So this design, this entire logic with rings and servers and everything is consistent hashing. Consistent hashing is a tool in a sense that it is a non-obvious idea, but once you know it, it is general and flexible enough to potentially prove useful for other problems. The idea has real applications. Consistent hashing gave birth to Akamai, which to this day is a major player on the internet, managing the web presence of tons of major companies. Even some of the bigger products like Amazon's DynamoDB and Cassandra is using this technique in their design. So if you like this video, please do like and subscribe to the channel. That would motivate me to make more videos like this. Till then, see you all.